All right, guys. So since you guys have taken chemistry, I am going to go pretty quickly through our review of chemistry. Make sure you're stopping and taking notes where necessary, and really slowing down if there's anywhere that you're a little bit confused. And of course, be sure to ask if you have any questions. Okay, so we'll start with the really simple stuff. Atomic structure. We're looking at three parts of an atom: the protons, neutrons, and electrons, which you should be pretty familiar with. In the nucleus, now don't get this confused with the nucleus of a cell, completely different scale, billions of times difference in size. So the nucleus of an atom is just referring to the center portion, which is where you're going to have the protons and neutrons. And then the electrons are negatively charged, and they are just buzzing by around the outside of that around the outside of the atom. So when we're looking at different types of elements, we care the most about the type of protons it has or how many it has. So as we build up the periodic table, you'll see 1, 2, 3, 4, etc. protons, and that is what defines each element. Now around those protons are going to be the electrons. And what do electrons determine? Well, they determine the charge of an atom. So if you change the number of electrons that you have, you change the charge of that atom. And so that is going to be what leads to the formation of ions. So a really classic example here would be sodium, which has 11 protons and 11 neutrons in its nucleus and 11 electrons when that atom is neutral. However, if you remember your rules of octet, that each shell has to have a full set of electrons, so 2 in the first shell, 8 in the second, 8 in the third shell. Then what we have in this case is a shell that just has 1 electron. And because that's problematic, as we will see in a moment, that's just going to yeet on out of there. And that's going to give us an atom with 11 positively charged protons, 10 negatively charged electrons, meaning that the loss of one of the electrons leads to a positive charge, because we now have more protons that are positive. On the flip side of this, when we look at something like, I think this is chlorine, 17 protons, 17 electrons, but for it to have a full octet, it's going to pick up an extra electron. That's going to mean it has now more electrons than it does protons, therefore more negative charges than it does positive. So if we're taking a look at our notes, now we know what kind of charges can cause from the gaining or loss of electrons. And so we need to identify the names of those types of ions. Anions are going to happen anytime you have an atom gaining electrons. And remember that gaining electrons means becoming more negative. On the flip side, cations are then going to form when atoms lose electrons. All right, so all of this talk about atoms, what we're really getting to is defining what matter is, and it's anything that takes up space and has mass. The smallest unit of matter that we study are atoms, and really, really important in this unit and in future units is that matter cannot be created nor destroyed. So keep that law of conservation of matter at the forefront of your mind. So when we're talking about matter, again, we're talking about all of those different elements, and the ones that you definitely need to be familiar with the abbreviations for are hydrogen, carbon, nitrogen, and oxygen. Those are the 4 that are the most commonly found in living things, as well as sodium, potassium, phosphorus, sulfur, and chlorine. Make sure you know all of those chemical symbols. Okay. So with matter, we'll usually be talking about energy as well. And this is a little bit more of a difficult concept for people to get. So I'll slow down a wee bit. So when we talk about energy, we're looking at the ability to move or change matter, to somehow affect matter. So matter is the actual stuff, and energy is the ability to somehow manipulate, change, move that stuff, that matter. And the 2 types that you need to be familiar with are kinetic and potential energy. When we talk about kinetic energy, we're talking about energy of motion. Kinetic energy happens anytime matter is actually in motion, and it can be in the form of electromagnetic energy, which is like sunlight and radiation. That is any type of energy that is traveling as waves. Mechanical energy would be kinetic energy of large masses that are all moving. And thermal energy, we'll see this one a lot too in this unit. Thermal energy refers to just random particle movement. So we measure thermal energy as temperature. And so when you think about thermal energy, think heat. Any energy that is not actively moving or being used is potential or stored energy. And what's important is that this energy can be converted into kinetic energy. It's just not currently being used. And a big example of that would be our chemical energy, because we're going to be looking a lot at different chemical reactions. And so the chemical energy that is in chemical bonds is super important. Now, the reason that happens, if you remember from your web quest on Friday, is if we were to take a molecule that is being held together with a bond and we came in and broke that bond, we have this really, really positively charged nucleus and another really, really positively charged nucleus of a different atom. So this over here would represent one atom, and on the left would represent a separate atom. And so when they are separated, those positive charges repel each other. So that potential energy is then converted into kinetic energy when they move in opposite directions. Okay, just like with matter, we're going to see a conservation of energy. So just like with matter, we know that energy cannot be created or destroyed, but there's a little bit of a caveat here. See, the amount of energy can't change, but the type of energy can. For example, we'll look a lot at photosynthesis and cell respiration in the next unit. So let's start visualizing that now, right? We can take the amount of energy in the universe and just change the type of it. We still have as much energy in the universe, it's just we're changing its form. In photosynthesis, we're taking solar energy, and that is getting converted into the chemical energy of plants growing, right? They're going to use that energy to help them build really complex molecules. And then we can take that energy and break it down for like our everyday activities when we're running or just maintaining homeostasis. And an important concept to understand about energy is even though the amount doesn't change, the amount of usable energy does. So I'll say that again, the amount of energy doesn't change, but the amount of usable energy does. So every single time there's any kind of energy transformation that occurs, there's going to be some that is lost as heat, and heat is just a not usable form of energy. Okay. So an important idea to understand is that matter is always going to be most stable when it has its relative lowest amount of potential energy. That doesn't mean it's absolute lowest, but as you can picture, if we were to take a ball and put it at the top of the hill, it's going to be the most stable when it settles down to the bottom of that hill. So we're going to see that when it's moving, the kinetic energy increases, and then as it rises up, more potential energy, and those numbers kind of fluctuate until eventually that ball settles down at the bottom, giving it the lowest amount of potential energy. All matter is going to follow that same trend. So let's go forward to looking at chemical bonds. Atoms are going to be stable only when all of their electron shells are full. We mentioned this a moment ago. And the reason for that is because that's the point at which there's a balance between the attraction of the electrons to the nucleus and the repulsion of those electrons to each other. So kind of like a rubber band, if you pull it, you've added potential energy. If you squish it, you've added potential energy. But when it's the most stable is when it's just kind of laying there, not stretched, not squished. The atom is going to act the same way. It's going to be the most stable when it has exactly 2 electrons in the first shell. Then once 2 are in the first shell, 8 can fit into the second one, and it's going to be the most stable when there are 8, exactly 8. And so on. And luckily for biology, we don't have to worry about any shells beyond 8 because the rest of the periodic table is too complicated for us biologists. All right, so we need to look at chemical bonding and how chemical bonding happens. So importantly, the outermost shell, we know that they always fill, the electrons are going to fill from the innermost shell and then fill outward. So that most outer shell is called the valence shell. And if the shell is full, that atom is stable. It has its relative low amount of potential energy, it is non-reactive. But anytime you have an atom that does not have a full valence shell, we're going to say that that atom is unstable and reactive, and it's going to do something to try to make sure that that valence shell gets filled. So when we take a look at things like these ions that we saw earlier, we have some ways of knowing what they can do. They can gain and lose electrons. They can also share electrons to fill up that valence shell. Again, just review, I hope. So we start with ionic bonds. Those are going to form anytime a cation and anion attract. And so again, cation is that positively charged. It has lost an electron. Anions are negatively charged. They have picked up electrons. And in the case of sodium and fluoride here, we can see that they're going to form an ionic bond because of the overall positive charge of the sodium and negative of the fluorine. On the side of the covalent bonds, that's usually what biologists care a lot more about. So covalent bonds means exactly that, co, or sharing, valent, meaning from the valence shell. So they are sharing electrons between two atoms. So over here, we've got oxygen. Oxygen's atomic number is 6, so it's going to have 6 protons and 6 electrons when neutral. Oh, sorry, that's wrong, 8. 8 protons and 8 electrons, 6 of which are in the valence shell. So if we take a look at this atom as it stands, it's not stable. It needs to react in such a way that it gets its valence shell filled. And it can do that by sharing an electron with, let's say, a hydrogen atom. Just like with oxygen, that hydrogen wasn't stable because it only had 1 electron. So by sharing a pair of electrons, the hydrogen's now happy. We can have the same process happen again, and we have now made a molecule. Woohoo! A molecule of, in this case, water. All right. So going on to chemical reactions, a really important concept is that when we talk about chemical reactions, there are going to be reactants, and those are rearranged into products, and that process makes up the chemical reaction. Importantly, whatever we're starting with at the beginning is what we end up with at the end. So all of the atoms that are there at the start are there at the end. Just like I rearranged the lines and whatnot to go from reactants to products, the same happens during chemical reactions. It's only the arrangement of the bonds that really matters. The atoms that are there at the beginning are going to be there at the end because we cannot create or destroy matter. So let's take a look at the combustion of methane. Methane gas is commonly used as like natural gas. And so it's combustible. And so we can take methane, CH4, and some oxygen, and we can have a chemical reaction occur. Notice that we're not gaining or losing any atoms. They're just getting a little bit reshuffled and then moved out of the way so we can see everything. So we've made some water, we've made some more water, we've made some carbon dioxide, but we have not changed how many atoms are present or the type of atoms that are present to make the product. Okay, so now we've come across a little problem. We need to remember an important idea. A full valence shell is stable and is unreactive. So stable molecules won't react. If we start with something like methane and oxygen and they're just sitting next to each other, they are not going to react because both of them have full valence shells in all of their atoms. They're happy, life is good. It's only when a chemical reaction, or it's only when a chemical becomes unstable that a reaction can occur. So here we've got methane. And like I said, all of the valence electrons that are in hydrogen and in carbon, they're all being shared and all of the shells are nice and full. That is a nice, super stable molecule. Okay, the only way that we can destabilize it is to be adding energy. So if it absorbs enough energy, then it can kind of shake loose all the different parts of the molecule in such a way that the bonds finally break. That is called activation energy. And most chemical reactions are started when there's some activation energy put in. It's just that little bit of energy that's needed, or sometimes a lot of bit of energy needed to get the reaction going. So without activation energy, the methane and the oxygen will just sit there. That's why when you light your stove, if hopefully you're using gas stoves, if you're doing this, don't light an electric stove on fire. But if you have a gas stove, that's why you have to have an ignition source. That's going to give just enough activation energy to break up the methane, to break up the oxygen molecules and allow them to react. Okay. So a common graph that we're going to look at here is a comparison of the reaction progress. So we'll have the reactants on the left, the products on the right, and the potential energy is the y-axis. And so the reactants have a certain amount of energy in them. Then to break them up, we need to add energy. That means that they have increased how much potential energy there is. They've gone to a higher energy state and they are now unstable. So addition of activation energy, that's how we get the molecules going. Then at this point, we can assume that we've done the same thing with oxygen. The oxygen's broken up and it's really unstable, and the hydrogens and the oxygens are all unstable together. And so what's going to stabilize them is to go back to having full valence electrons, having full shells, and that means that energy is going to be released as they become stable again. So the formation of new chemical bonds is going to then release energy. So we start with an amount of energy. Energy has to get absorbed for the molecule to fall apart enough to want to react. And then once they've become stable again, the released energy is, no longer part of the molecule itself. And then the difference here between the reactants and what we have at the very top of this graph, that is the activation energy. Okay, so energy changes in reactions, they're not always going to start and end the same way. In fact, most chemical reactions have either more energy at the beginning or more energy at the end. So we have two types of reactions that we'll talk about. First, endergonic and then exergonic reactions. Endergonic and exergonic, they are opposites. So in the case of endergonic, what that means is that energy is going in. Okay, so we looked at the beginning with the conversion of solar energy into chemical energy, which happens during photosynthesis, right? In this case, what we've got are a whole bunch of reactants, carbon dioxide and water coming from the air and the ground. And those are really low energy molecules. They don't have a lot of chemical bonds. There's not a lot of energy there. And so what has to happen is energy can get stored. And so the sunlight is going to be used to make the bonds. So solar energy converted to chemical energy. And now take a look at this guy. This huge molecule here is a sugar and it's full of energy. So we say that it's got a lot of chemical energy. So solar to chemical has happened. And so endergonic reactions, that's that kind of reaction where we've taken energy and we've put it into the chemical bonds of a molecule. That means we have a lot more energy in the products than we did in the reactants. And this happens anytime you're building large molecules. So when we look at an endergonic reaction, we can kind of graph it like this. We've got a lot of activation energy, right? We have to break up these small but stable molecules, break them up so that they'll react in such a way to make these much more complex molecules like the sugar molecule, really complex. So that is the activation energy. It's really high. And we see the products have a lot more potential energy than the reactants. So just as you can probably guess, then an exergonic is going to be mostly the reverse or the opposite. We have energy out is literally what it means, exer or exiting. The energy is leaving. Before we looked at the example of breaking down sugars to be able to run. And that's an example of an exergonic reaction. We start with a high energized molecule. We break it all down. That energy is then used for something else. And that means we have a lot more energy at the beginning in the reactants than we do in the products. The reactants are high energy, the products are low energy. And so this is common when we're breaking down molecules. And there is our graph. A lot of energy at the beginning, doesn't take too much activation energy to have those molecules break apart and become reactive, and then go into a much more stable configuration in the reactants, much smaller, much less chemical energy there. Okay, if you didn't get any part of your notes, make sure to ask. And if you're confused about anything, rewind or ask. Otherwise, that is it for our chemistry